Good morning, students. I hope you all are well and doing mathematics comfortably. These days, we people are doing linear algebra, and under this heading, we have done vector space, vector subspace, and linear combinations. Today, we will extend this concept. So, let us see. Let V be a vector space over the field F. If V1, V2, V3 belongs to V and C1, C2, C3 belongs to F, then C1 V1 plus C2 V2 plus C3 V3 CK VK is called linear combination of vectors V1, V2, V3, Vk. Definitely this is the member of V, because we people know that V1, V2, V3 up to Vk, these are the vectors, and this V is closed under addition as well as the scalar multiplication. So definitely this expression will be the member of V. So if these are the vectors and these are the scalars, so if this expression, this one, it is written like this. So this expression is known as the linear combination of vectors, this and this. Okay. Now remember, we have developed this concept with the help of several examples. Now sometimes these elements are written in the form of set. So I repeat this one. Let and obviously S is a subset of V. Then C1 V1 plus C2 V2 CK VK is the linear combination of elements of S. I have rewritten the previous one. So if this is a set having these members, obviously this is a subset of this one. This expression is a linear combination, but I write C1 V1 C2 V2. This is a linear combination of elements of S. Now if we write all the linear combinations and we make a set of linear combinations, then that set has a particular name, that is span of S. So the sets consisting the vectors, the set consisting the vectors which are linear combination of the elements the set consisting the vectors which are linear combinations of the elements of S, that means C1 V1 plus C2 V2 CK VK. Remember, this is the element, and you remember this is a vector which is a linear combination of V1 V2 up to Vk. So the set means this one consisting the vectors, since this is a vector, which are linear combinations of the elements of S. Here C1, C2, Cn, or Ck belongs to F or whatever it is. So this set is called, that means this, the set consisting the vectors which are linear combination of the elements of F, that means this is called the span of S. Okay. Therefore, and span of S is denoted by, therefore, what is span S? It is the set of linear combinations. So it is C1 V1 plus C2 V2 such that C1 C2 up to Ck belongs to. So this is the set of linear combinations. Okay. You try to understand. Suppose I write S equals to, recall the previous example. Suppose I write 3 0 and 0 5, for example. It is this. And V equals to R square. So definitely these two members are the members of V. So here S is a subset of V. Now I write 7 comma pi equals to, this is 3 by that is 7 by 3 3 comma 0 and plus 0 comma 5. See, this is 7 comma 0 and this is cancelled out, and you find this is pi, so here it is written. So 7 comma pi is the member of this. So 7 comma pi is written like this. That means 7 comma pi is a linear combination of 3 comma 0 and 0 comma 5. Therefore 7 comma pi is the member of span S. Okay. That means 7 comma pi belongs to span S. Similarly, we write one more example. Suppose I write 12 comma minus 10. Also, then I write it is in terms of 4, so 3 comma 0 plus minus 2 times 0 comma minus c. Check the calculation. 4 is at 12 comma 0 and this is yes. Therefore, 12 comma minus 10 belongs to span of this. समझ में आ रहा है? So what do you mean by span? Span is nothing. Span is a set of vectors, and these vectors are the linear combinations of the elements of S. You remember the elements of S, here I have written two elements, that is one is 3 comma 0 and other is 0 comma 5. And this is a subset of R square, two dimensional. So this is a subset of this. Now there are infinite number of members of V. You remember 3 comma 0 itself is written in the combination, linear combination of these two. That means you can write, it is already written, you can say this 3 comma 0. I can write it is 1 times 3 comma 0 plus 0 times 0 comma 5. You can say this. 1 and 0 are the scalars. So 3 comma 0 is also the member of span of this. Be careful, 7 comma pi is not the member of S here. Be careful. 7 comma pi is the member of span of S. See the difference. The set S and span of S. Span of S is the set consists the vectors which are linear combinations of the elements of S. Okay, so here you can say 7 comma pi is not the member of this. 7 comma pi is the member of span of this one. So you can say 12 comma minus 10 is also the member of this one. So if 12 comma minus 10 is written as a linear combination of 3 0 and 0 5, then 12 comma minus 10 will be the span of this. Now the next question is, I will extend this question. Can we write, listen, can we write every member of V is a linear combination of these two? If it is possible, then the set S is called spanning set of V. That means V is spanned, विस्तार जिसको बोलते हैं स्पांट, ये बालिस्त स्पांड फैल रहा है ये. Then S is called spanning set of V, or V is spanned by V is spanned by S, or S spans to V. So again you listen. Can we express every member of V as a linear combination of these two? That means, can I write span of S equals V? If it is possible, then this set is called spanning set. So let us say, this is the question. Now simplify this. Here for every x comma y belongs to R square, we find C1 C2 belongs to R scalars. So we find C1 C2 belongs to R for every x comma y belongs to R such that x comma y equals C1 3 comma 0 plus C2 0 comma 5. For every xy belongs to R square, if we find these two scalars such that this is written as a linear combination of this. So this is x comma y, so it is 3c1 plus this is 5c2. This implies x equals to 3c1 and y equals to 5c2. This implies c1 equals to x by 3 and c2 equals to y by 5. Yes, we have c1 and c2 because x and y are real numbers. Therefore, x upon 3 and y upon 5 both are real numbers. So, we found C1 and C2 in such a way that every member is a linear combination of 3, 0 and 0, 5. Therefore, every member of V R square is a linear combination of 3, 0 and 0, 5. Therefore, the span of S equals to V, that is R square. Therefore, S is the spanning set of V. S is the spanning set of V. So sometimes the definition is asked, what do you mean by spanning set? Remember, span of V and spanning set both are different. So if span S is equal to the given vector space, then S is called the spanning set of V. That means, or I can say V is spanned by S with or S spans V, or I say S generates V, पैदा करता है. In the broad language, you can see S spans V, S generates V. But when span S is equals to V, then this is called the spanning set of V. Okay, so it is like this. Note, the most and the natural spanning set of R square is 1, 0, 0, 1. The most and the natural spanning set of R square is this one. Why? Because for any x comma y belongs to R square, you can consider any member of R square that is written in this particular form. So every member is a linear combination of 1, 0 and 0, 1. In two-dimensional, you people know that is unit vectors along x-axis I cap and along y-axis, that is j cap. So the most and the natural spanning set of R square is this one. In a similar way, I hope you can understood the natural spanning set of R cube is, I hope you can write 1, 0, 0, 0, 1, 0, 0, 0, 1. It will be this. Okay, reason you people know that for any member x, y, z belongs to R cubed is written like this. So it is x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. So this is a spanning set, but you remember this is a natural one. It doesn't mean that we have only 1, 0 and 0, 1, or here we have 1, 0, 0, 0, 1, 0, 0, 1 and so on. We may have other spanning set also that generates the R square as well as R cubed. Now you remember these are the questions. You have to verify set S is given, only one member is given, is as a spanning set of R cubed and all this. Okay, so now first one I solve for this. S equals to 1, 1, 1 is as a spanning set of R cubed. You just see. If possible, let x, y, z belongs to R cubed such that this implies it means this is not true for all. If I write let 1 comma minus 1 comma 2 belongs to R cubed. Now if possible, write 1 minus 1 2 c times of 1 1 1. So this implies c equals to 1, c equals to minus 1, c equals to 2. This is not possible. We find absurd results. So this is not the spanning set. This is not the spanning set. But you can write the numbers. Suppose I write 2, 2, 2. This you can write as 2 times of 1 1 1. So this is the member of span of S. So here it is 2 2 2 belongs to span of S. Yes, because I can write this one as a linear combination of this one, but I cannot write the every member of R cubed as a linear combination of this one. And if we consider it geometrically, then you find the answer is so simple. The line passing through this is 1 1 1, this I say 2 2 2, so on. So the points lying on this line are linear combinations of this one, and this line is the part of three-dimensional space, that is R cubed. This is the part, means the points lying on this are the linear combinations of this one, not other points. Therefore this does not span the R cube. So geometrically you can find the answer of this. So you just verify, you just find the answer of this one. So thank you very much. Jai Hind.